So I'm not sure if we're going by order on the list, but I think I'd be first on the list. Is it with me sharing screen, putting up slides before we go live, or shall I wait until we go live?
It doesn't matter. I mean, you can prepare your slides if you like to. It's okay.
Okay, well, I'll wait then until we go live officially.
Okay.
So the stream is online. So we can start on time, I guess.
Okay, good, excellent. Okay. Welcome everyone to, what is this, session C2 of ICALP. There are 6 papers in this session, so we'll take about, we'll go in order, and we'll start with a short presentation and then we'll have a discussion. So the first paper is Symmetric Arithmetic Circuit by Anuj Dawar and Gregory Vilsenach, and Gregory will give the talk. So please go ahead.
Okay, right. Let me just quickly share my screen. Let's check if that's, is that working?
Yes.
Okay. Okay, great. So I'm talking today about some work done with Anuj Dawar on symmetric arithmetic circuits. Oh, sorry there. Okay, so in arithmetic complexity, there are these 2 complexity classes of particular interest, VP and VNP, and the central conjecture is Valiant's conjecture, which asks whether they're actually the same. Within these 2 families are 2 particular families, within these 2 classes are 2 families of particular interest, the permanent and the determinant. The permanent being VNP complete, the determinant being VP complete under a different reduction. And Valiant's conjecture is equivalent to asking whether there are superpolynomial lower bounds in the size of arithmetic circuits representing the permanent. And just like in circuit complexity, one standard approach for making progress in this problem is to consider restricted circuit classes and to try to prove lower bounds in these restricted cases. So what we did was consider sort of a natural notion of, we sort of introduced a novel restriction based on sort of natural notion of symmetry for circuits. And so we started off by considering polynomials and symmetries of polynomials. So we say some polynomial is G symmetric if it's symmetric under the action of the group G on its variables. Sorry, invariant under the action of the group G on its variables. And we consider the permanent and determinant families with respect to very particular groups. So in the case of the permanent, we look at the symmetries, the group of symmetries given by row and column permutations. And in the determinant, we look at symmetries given by simultaneous row and column permutations and transpositions. And so we say some circuit representing a G-symmetric polynomial is symmetric if every permutation in G, which has some action on the variables and hence induces an action on the input gates, extends to an automorphism of the circuit. And in this model, we separate the permanent and the determinant. So we show that there's a polynomial upper bound for the determinant and a superpolynomial almost exponential lower bound for the permanent. So more concretely, we prove for every field of characteristic 0 that there's a family of symmetric arithmetic circuits of cubic size representing the determinant. And for the permanent, we show that for every field of characteristic not equal to 2, there's a superpolynomial almost exponential lower bound for representing the permanent. And of course, you can't do any better than characteristic 2 because over characteristic 2, the determinant and the permanent are the same. So in that case, we have the best possible result. So that's it. Those are the 2 main results. Are there any questions?
Yeah, so I think there were some questions already posted on the Slack channel, but maybe we can start by taking some other questions from the audience. So please either feel free to speak up or you can type it in the chat box if you prefer.
Okay, let me get the chat box up there.
Okay, so I have a question which is essentially also a follow-up question on the one that I asked on Slack. So for the determinant and for the permanent, you use different groups, right? So the group for the determinant is much smaller, which is of course in some sense needed because for the determinant, you need that the product of the determinants equals 1. But would your lower bound also say hold true if you enlarge the group? So could you prove an exponential lower bound for the determinant when you enlarge this group? So you could have permutation of rows and columns, but you want that the sign of these permutations is simply the same. Right? This would still be invariant to determine that this action. And could you prove lower bound against the determinant in this model?
So for example, if you were to take some larger subgroup of the stabilizer group of the determinant, could you prove a lower bound, an exponential lower bound? Yes. We don't know. So I mean, as you note, we prove the determinant for a reasonably small group, for the particular group we pick, and that's because we can't find we couldn't find other techniques which were symmetric. So we couldn't prove the result in the stronger way. So we're not sure whether our upper bound would hold if you took the entire stabilizer group for the determinant. So that remains an open problem for us.
And for the lower bound, where do you use that you have, say, the permanent and maybe, so there are some lower bounds, exponential lower bounds against the determinant, but you can also prove them against the permanent, that you can also prove against the determinant, which then doesn't tell you that the permanent is hard, but that the model is weak that you're using. So the question is, in your model, so when you prove the lower bounds against the determinant, against the permanent, I'm sorry, where do you use the fact that this is the permanent and not the determinant?
Well, that's a good question. So it's really important in this case. So you're entirely, I mean, we first comment on the fact that you're entirely right. In many cases, the model doesn't actually separate the two. So here we use the fact that it's permanent because what we do is we establish a translation from arithmetic circuits to Boolean circuits. And so then what we need to do is show a lower bound in the Boolean case. And the result is that because we use here the connection between the permanent and the problem of showing the counting number of perfect matchings in a bipartite graph. And so it turns out in the Boolean case, what we need to do is show that the counting width of the graph parameter, which counts the number of perfect matchings in a bipartite graph, is linearly bound, is bounded below, is at least linear. So sorry, I'm getting a bit ahead of myself. The concrete answer to your question is the thing we use about the permanent that we don't use about that doesn't apply to the determinant is we use the fact that the permanent of a 0-1 matrix is equal to the number of perfect matchings if you interpret that matrix as giving you as being the biadjacency matrix of the bipartite graph. And so we therefore, and then we actually prove the lower bound by proving a lower bound for this count on number of perfect matchings.
I have a basic question. So is there any sort of natural formula for the permanent that does not satisfy your definition of symmetric?
I mean, we looked around a bit for that. I actually don't think so. I mean, the standard formulas that are given for the permanent, I mean, the most standard one that's used everywhere is Rice's formula, Rice's formula, which is symmetric, which does give a symmetric family of polynomials. So I don't know enough about whether there are. I mean, there may well be other formulations which are not symmetric, but the standard ones.
Well, there is the sum of product expansion of size and factorial. I guess that's Yeah. Okay. Good. So, are there any other questions? Any other discussion related to this paper? Okay. Well, thanks, Gregory, for the nice presentation. So we will be moving on to paper B. So paper B is by Armin Weitz, and it's on hardness of equations over finite solvable groups under the exponential time hypothesis. So Armin, please go ahead.
Hey, yeah. Hello, everyone. Can you hear me?
Yes.
Yeah, good. Okay, so thanks for the introduction. So I will share my screen, at least try. Okay, so there it is. Okay. Yes, so it's about hardness of equations over finite solvable groups. So in the paper, I considered two problems. So the equation satisfiability problem and the equation identity problem. And so in both cases, we have a fixed group G, and then the input is an expression over group constants or variables. And the question is for the satisfiability problem, whether there is a satisfying assignment, and the identity problem, whether all assignments are satisfying. so that the expression evaluates to 1 in the group. And previously, there have been some results. For nilpotent groups, it's all easy. And for non-solvable groups, the problem is NP-complete or co-NP-complete. And there also have been some partial results for solvable but non-nilpotent groups. So some special cases of fitting length 2, they are also in polynomial time. And well, in this paper, I give some lower bounds for some other solvable but non-nilpotent cases. And so the main theorem is we have a finite solvable group and fitting length is 4, or it's 3 and some other extra condition hold. And then if we believe the exponential time hypothesis, the equation satisfiability and equation identity are not in polynomial time. And just to recall, the fitting length is the smallest k such that we have a series like this with all the quotients being nilpotent. So it measures somehow how far is a group from being nilpotent, or with other words, how far is it from being abelian. And just a few words on the proof. It's by a reduction of the C coloring problem to the satisfiability problem. So if we have a graph, we produce some equation, and the equation is satisfiable if and only if the graph is C colorable. And this equation is somehow small. So it's 2 to the square root of number of edges. So a little smaller than 2 to the number of edges. And it can be computed somehow efficiently. And now if we assume that equation satisfiability is decidable in time 2 to the little o of log square n, then we get a contradiction to ETH. We just plug in this n equal to 2 to the square root of e, and then we can solve the C coloring problem in time 2 to the little o of e, and that contradicts ETH. Okay, so that's the basic proof idea, and well, so we give a quasi-polynomial lower bound, and of course, now the question is also whether there is a matching upper bound. Yeah, and also question what about groups of fitting length 2? Okay, are there any questions?
So yes, we have one question on Slack by Anuj Davar, and Anuj is here, so perhaps you would like to ask the question in person.
Sure. I mean, I was looking at the definition, and so for a fixed finite group, this SAT problem is a finite domain constraint satisfaction problem. Is it not? And so does it not fall under the Bulatov-Zhuk dichotomy?
So I don't know the precise definition of the constraint satisfiability problem, but it somehow, apparently it does not fall under this dichotomy. So
I mean, it looked to me like, so you have, essentially you have a finite domain, which is the group elements.
yes,
I give you the string, so I put a variable for each prefix of the string, and now I have an equation for every prefix, which basically says the variable multiplied by the next element gives me the next variable. And now I'm looking for a solution for the system of equations, and that's so that makes it a constraint satisfaction problem. It looks to me like it should be, but this is why I'm puzzled, because you seem to be getting some. I mean, your conjecture there at the end suggests there's something intermediate between P and NP complete, which Bulatov-Zhuk dichotomy suggests there shouldn't be for constraint satisfaction problems.
yes. So yeah.
I mean, maybe this is one to discuss offline, but I mean, there seems to be something.
Yes, there seems to be something. So there's other paper at LIX by Pavel Ijak and co-authors. So they might be able to tell you something more about this constraint relation to constraint satisfaction problem. They have some similar results also based on ETH. And yeah, so I don't know, I'm not so familiar with this constraint satisfaction problem, so sorry.
No, that's all right.
May I?
Ah, you're here, Pavel.
The problem is that there is a big difference between system of equations when you have the external conjunction to combine those equations into the system of equations and a single equation. That's interesting, but having a single equation, you have a bigger expressive power. So everything which is expressive for a certain, template over CSP can be expressed by a single equation, obviously by a system of equation as well, but not conversely. So in particular, this proves that that under ETH there is no correspondence between CSP and equation solvings.
So, I mean, could you go back to the slide which had the definition of equation set? Maybe I'm missing something here.
So we are given
the expression has G and X. So X are variables and G are group elements.
Yes. But it's a single equation.
But it's a single equation. So, I mean, my proposal was to turn this into a system by introducing a variable for every prefix of this expression alpha, right?
Okay, yes.
And then for, so if you have a prefix X and then X plus 1, you basically say that you get an application of, by an application of the, you get to the next prefix by an application of the group operation.
But if you introduce a system, doesn't that mean that sort of the same variable must always appear into consecutive equations? So doesn't that restrict the sort of the CSP instances?
So I suppose there's something to prove that every solution to the system still gives you a solution to the original one. But okay, I'll take your word that there is a gap between these, but I'll have to think about it.
Yeah. So for systems of equation, there is also this dichotomy. So there it's it's NP, or for non-abelian groups, it's NP complete.
Yep. I see. Yeah. Okay.
Okay.
Thank you. Sorry.
Okay. Well, thanks for the interesting discussion. Are there any other questions about paper B in this session? Okay. Well, thanks Armin for the nice presentation and also for your cool demo in the video. So we'll move on to paper C, which is paper C is by Tony Pitassi, Morgan Shirley, and Tom Watson, and it's about non-deterministic and randomized Boolean hierarchies in communication complexity. And I think we have Morgan here, so please go ahead and tell us a bit about the paper.
Am I sharing my screen?
Yes.
Okay, good. So I'll give a brief overview of the paper to remind you of the talk. We are interested in problems in communication complexity. In communication complexity, we have two parties, Alice and Bob. They each get some input and they exchange messages in order to solve some function on their inputs. In this talk, we'll just be considering functions over a Boolean domain. And they're allowed unlimited local computation power, but they are charged for the cost of the number of bits that they exchange during the communication phase. This is the deterministic model of communication complexity, and it's the standard one. We can also consider some extensions. One is randomized communication complexity, where they're allowed some random coins, and they must answer correctly with high probability. There's non-deterministic communication complexity, where there's some all-knowing prover who sends a witness to Alice and Bob to convince them of the value of the output. And there's communication complexity with an oracle, where Alice and Bob can send messages back and forth as normal, but they also have access to an oracle where they can query the oracle and get a response back that for some function that is in the class that the oracle represents. So in this example here, we have a non-deterministic oracle. Alice and Bob could query the non-deterministic oracle for some function in NP and get the answer back for that query. So we have all of these classes. One that I didn't mention before, but is important for this talk, is one-sided randomness. So we call this RPCC. And you can imagine we can build even more and more complicated classes like this by stacking oracles upon oracles. And in fact, there are some interesting applications of this. The communication complexity version of the polynomial hierarchy has some deep connections with the rigidity of explicit Boolean matrices. But unfortunately, our toolbox isn't good enough to deal with this. We don't even know, for example, how BPP and P to the NP, two relatively simple classes, we don't even know how these are related. We do know the answer if partial functions are allowed. So if X and Y are sampled from a non-product domain. But for total functions, we do not know how they were related. To make progress towards this, it's interesting to consider the probably easier problem. Does BPP equals P to the RP, which is strictly contained in P to the NP. Our paper makes progress towards this by looking at the situation where we limit the number of oracle calls to the RP oracle. So the classes you should consider here are the classes that are notated thusly. I pronounce this P to the NPQ parallel, and what this means is that it's a deterministic protocol with an NP oracle, where we restrict it such that there are at most Q oracle calls, and the oracle calls must be made in parallel. We can also consider replacing this NP oracle with an RP oracle. For NP, these classes are sandwiched between what the layers of what is called the Boolean hierarchy. We call it here the non-deterministic Boolean hierarchy because we also consider a modification called the randomized Boolean hierarchy. This has been studied in communication complexity before, and it is proved that this hierarchy does not collapse. So more calls to an NP oracle helps compute more functions. So if we replace these NP oracles with RP oracles, we get the randomized Boolean hierarchy. And our paper shows that this is also infinite. So more queries to an RP oracle help compute more functions. There are also some small gaps in previous work here between certain classes. Where we previously were not quite sure of the connections between classes. And we closed those gaps for both the non-deterministic and randomized Boolean hierarchies. Here are some open questions, and I would be happy to take questions. I think there was one in the Slack previously.
Right, so we can start with that, Marcus.
Okay, yeah.
So as you said, so this separation result only holds for a constant number of queries. And
Correct,
so the
yes.
question is, so what is the reason for this? So where does the proof break down, or why can't you separate 7 from 8 questions, but not log n from log n plus 1 or something like this?
So our proof technique for having a lower bound against the class NPQ involves taking a subset of the inputs, and we say that this subset of the inputs is answered incorrectly by the first k NP subproblems. So if we take the computation represented by the first certain number of NP subproblems, this will answer incorrectly on all of the inputs in this set. And as we continue, we refine this set, but we need to refine by quite a bit. So the dependence ends up being exponential in the number of times we refine the input. So since we need to do it q+1 times, this is exponential, and we need it to be a constant. So 2 to a constant is a constant, but anything worse than that, we don't know how to deal with.
Okay.
Good. Are there any other questions? So is it possible? Yes, please go ahead.
So no, this was just another question, but I forgot about communication complexity. So you make your model is non-adaptive, right? So you have to ask the queries all in parallel. Does it make, or what's the difference if you are not adaptive? So if you are adaptive, sorry, so you can you don't have to ask these questions in parallel.
So certainly you can simulate adaptive queries by non-adaptive queries, but you get an exponential blow up. So at constant levels, it still should be fine, but yeah.
Okay.
Is there a way to describe what these hard functions look like?
Yeah, the hard question is so equality is a function that is easy for one-sided randomness in one direction, but hard for even so it's easy for co-RP, but hard for NP. Essentially, what you do is you take Q independent copies of equality and ask for the whether an even or odd number of the answers are yes.
Thanks. Any more questions about paper C? Okay, well, thanks, Morgan, for the presentation and for answering the questions. So we'll be moving on to paper D, which is by Mohammed Mahmoudi, Caleb Smith, and David Wu, and it's can verifiable delay functions be based on random oracles? So I think we have both David and Mohammed here, so please, one of you. Okay, David, go ahead. And...
Yeah. Cool, thanks, Andre, for the intro. So can you all see the slides?
Yes.
Cool. Okay, yeah, so as Andre mentioned, I'll be talking about verifiable delay functions and whether they can be instantiated in the random oracle model. This is joint work with Mohammed Mahmoudi and Caleb Smith. So a verifiable delay function at a high level is a deterministic function that takes a large sequential time p to compute. But once it has been computed, there's an efficient verification algorithm that takes the input, takes the computed output, and possibly a proof, and tells you whether the computed value is correct or not. And this verification algorithm is very efficient, runs in time much faster than the time it takes to compute the function. So since their inception, verifiable delay functions has found a number of applications in cryptography to randomness beacons, proofs of replication, computational timestamping, and many more. And as such, many works have focused on constructing a verifiable delay functions from a wide variety of cryptographic assumptions. If we look at the existing list of cryptographic assumptions on which we can construct verifiable delay functions, though, we'll see that all of them require some kind of algebraic structure. A natural question then is to ask whether some kind of algebraic structure is actually inherent in these constructions. And we ask this question because for a very closely related primitive to verifiable delay functions, namely proofs of sequential work, we can actually realize them from unstructured assumptions. So it is natural to ask whether the same is possible in a setting of verifiable delay functions. And in this work, we're going to model unstructured assumptions by access to a random oracle. This is a canonical model in cryptography that models the hardness from things like one-way functions and related primitives. And in this work, we provide several lower bounds or negative results, ruling out the possibility of constructing certain types of verifiable delay functions in a random oracle model. Our first lower bound rules out the possibility of constructing verifiable delay functions that satisfy a notion called perfect uniqueness in a random oracle model. Perfect uniqueness basically means that for every input x to the verifiable delay function, there's at most one output y that will cause the verification algorithm to accept. So such VDFs cannot exist in a random oracle model. These were previously constructed under that term reversible proofs of sequential work from algebraic assumptions. Our second lower bound rules out another class of verifiable delay functions. Here we rule out VDFs that have a tight sequentiality guarantee, namely even a parallel adversary whose running time is just slightly smaller than the running time of the honest evaluation algorithm should not be able to construct a VDF. So this is a very difficult regime in which we can construct VDFs. Such types of VDFs cannot be based solely on the random oracle model. However, our results still do not rule out the full possibility of constructing a VDF in a random oracle model. It only rules out these specific subclasses of verifiable delay functions. And I think another way that you can view these results is that if we were to try and build a VDF in a random oracle model, if we are looking for a positive construction, somehow we have to circumvent these barriers that we have identified. In particular, it must be non-tight, and we must have a weaker notion of uniqueness. Of course, we do have many constructions of VDFs from algebraic assumptions that avoid these kinds of barriers, and our work leaves open to still the possibility of building them in a random oracle model. So I think both of these, the positive and the negative results, seem plausible and might be of great interest for future work in designing better VDFs for better understanding their hardness. And with that, I'll conclude. Thanks.
Sorry, I was muted. So thank you, David. So we can take some questions now. Please, anyone from the audience can ask, and then we can take the question from Slack. So please go ahead. So I think there was again one question by Marcus on. There are several questions on Slack. Yes. So please go ahead.
Okay. So. This is, but somehow I'm a little bit biased. So whenever something has a group inside, it's called algebraic, and otherwise it's not called algebraic. So, so my question is simply, so what do you mean by algebraic assumptions? Is there some formal definition, or is it just a not random oracle model?
Right, that's a great question. So this is kind of used in an informal context, oftentimes in cryptography. So essentially a random oracle will capture sort of the extreme end of unstructured assumptions. And if you have a lower bound in a random oracle model, then that says that you need some additional kind of structure in order to realize the primitive. But there's no formal mathematical notion of what it means to have algebraic structure. Another way that I think you might be able to view it is you can say that assumptions that have algebraic structure give you public key encryption. Unstructured assumptions give you one-way functions or symmetric key cryptography. So you can view it as mini-crypt primitives are unstructured, cryptomania primitives are structured. So that's another potential way to view it, but there's no formal definition for what it means for an assumption to have algebraic structure. There are idealized models that do capture these additional kinds of assumptions. So for instance, the generic group model will capture the hardness implicit in certain types of groups. But for other kinds of assumptions like lattice-based assumptions, we don't have an abstract model or an idealized model that captures that kind of structure.
David, can you give some example of a VDF that has computational uniqueness but not perfect uniqueness?
Yeah, so actually all of the existing constructions, with the exception of the proofs of the reversible proofs of sequential work, actually provide computational uniqueness. So computational uniqueness basically says that no efficient adversary can find a proof that causes the verification algorithm to accept with respect to a different output other than the one computed by the honest evaluation. So all of the existing constructions, except the work by Musala et al. From Eurocrypt last year, are actually in a regime of computational uniqueness. So that's actually the more common mode of constructing verifiable delay functions.
So the one that I have in mind is this Kirchak and Veselovsky g to the 2 to the t. So isn't that, I was under the impression that that falls under perfect uniqueness, because if you claim a different output, then, I mean, isn't soundness violated even by an inefficient prover, or?
Not quite. So there is a unique output in the sense that if you run the honest evaluation algorithm, like if, let's say the verification actually runs the honest evaluation, there's only one output. But if we want the verification algorithm to be fast, then the way that there's basically a proof that the verifier will check, right? And that proof only provides computational soundness. So there is only one unique value, but you could find a proof that causes the verifier to accept for a different value.
Okay.
So that's what computational uniqueness refers to.
So when you say find the proof, you mean find a written proof in the random oracle model, or with sort of or an interactive proof?
Non-interactive proof. So
not interactive. I see. So this is about okay. Then,
yeah,
then,
it's just
then,
that
then
basically there's an argument that the value.
Then I believe it.
Can I add one comment here? So
yes.
David gave an excellent answer. Basically, some of these constructions first are interactive, and for the interactive version, you might have statistical uniqueness. But once they want to make it non-interactive, they apply the so-called Fiat-Shamir transformation, and then that's actually going to make it computational, because then you lose that guarantee of statistical. That's but
does your lower bound capture sort of even interactive certificates, or only
no, it's only for non-interactive.
Only for non-interactive certificates. Okay, interesting. Well, thanks. Any other questions? Okay, well, thanks for David for a nice presentation, and Mohammed for pitching in to clarify. So we'll move on to paper E in this session. It's by Thomas Hakoniemi, and it's on feasible interpolation for polynomial calculus and sum of squares.
Okay, thank you. I will share my screen quickly. Okay. So I hope you can see the slides now.
Yes.
Okay, so yes, so my talk was on feasible interpolation for polynomial calculus and sums of squares. So let's just quickly recap what is feasible interpolation. So it's a framework for reducing length of proofs lower bounds in proof complexity to lower bounds on computational models. It was introduced by Krajicek in the 90s, and the basic idea here is that if we are given a refutation of this kind of conjunction that has some common string Z of variables between the conjuncts, the idea is to translate this given refutation into a somehow efficient algorithm that computes an interpolating function for this conjunction. So basically a function that, given an assignment to the variable Z, tells whether P or Q is unsatisfiable when Z is replaced by the assignment, and then use non-computational lower bounds to obtain lower bounds on the proof size. Okay, and the form of feasible interpolation I proved in this work is as follows for two systems. So first for polynomial calculus. So not only is the interpolating function computable in polynomial time in the length of the given refutation, but one can actually find a refutation for one of the conjuncts, basically. Okay, so here P and Q are two sets of polynomial constraints, and we make this claim only for a finite field. I noticed there was a question about this in the Slack, so I'll answer that later. And for sums of squares, we have, again, a similar kind of a result that we can find a refutation of one of the conjuncts given the refutation of the conjunction. Okay. So what's the proof outline here? Both proofs follow a very similar kind of a pattern. So first of all, we make kind of a shift in focus from proving size upper bounds directly, because we want size upper bounds here for the proofs of one of the conjuncts, to proving the existence of refutations over some small set of monomials. So we define a notion of proof over a set of monomials. Okay, and this shift is important for the second item here, because this shift allows us to give nice semantic characterizations for refutations over a set of monomials, and then prove kind of a soundness and completeness theorem for resource-bounded refutations. Okay. And thirdly, using such semantic objects, we can prove what I call feasible disjunction property for polynomial calculus and sums of squares. So this is an existential statement about the existence of a refutation. So given this refutation of this conjunction, we can from that define some small set of monomials that either one of the conjuncts must have a refutation over that small set of monomials. And finally, we argue that okay, this refutation, whose existence is guaranteed by the feasible disjunction property, can be actually found in time polynomial in size of the set of monomials, and in the case of sums of squares, in the size of the coefficient in the given refutation of conjunction. Okay, and conclusions. So this form of feasible interpolation, even though it's quite strong, it's not strong enough to give actually new lower bounds for the systems, but they give new information about the relative strength of the systems considered. Namely, they show that basically these systems are in some sense much closer to, say, resolution than some stronger proof systems. And just to note that a very similar proof as in sums of squares gives a feasible interpolation for Shirley-Adams, even though we have not considered it in the paper. Secondly, or thirdly, it's a question about monotone feasible interpolation. So monotone feasible interpolation is a question: if the interpolating function is a monotone function, can one always transform a small proof or a small refutation into a small monotone Boolean circuit computing the interpolating function? And for sums of squares, we know that this cannot be the case, because sums of squares has small proofs of the click coloring formulas that then would contradict the known exponential lower bounds for monotone circuits. But for polynomial calculus and Shirley-Adams, this is completely open. And then there's much more vague question is whether a similar idea of using semantics for resource-bounded refutations could be actually used to prove feasible disjunction property for stronger systems, even for systems that we know that cannot have feasible interpolation. So thank you. This was my short introduction.
Okay, thank you very much, Thomas. So Marcus, perhaps you could go and ask your algebraic question.
That's not really algebraic. So in the first feasibility result, as you said, it only works over finite fields. And so my question is, what is the reason for this? Why doesn't it work over the rationals or something like this?
Okay. So the reason is this algorithm. So this would need further analysis, because so the algorithm goes. So you start with the constraints. but you are constantly in the adding new polynomials into the constraints. And by choosing the polynomials stupidly, you might, every time you add constraints, double the maximum coefficient basically in there. So you might end up quickly with, say, doubly exponential coefficients there.
Okay, so you only need the finiteness of the field to control the size of the coefficients, essentially.
Yes.
So
for rationals or reals, this needs really a more careful analysis and maybe a more careful choice of the polynomials involved there.
I see. So thanks.
Thank you. Any other questions from the audience? Please feel free to speak up. Okay, well, thanks, Thomas, for the presentation. So we have one more paper left in this session. It's paper F by Xiaoming Sun, Yuan Sun, Jiaheng Wang, Cohen Wu, Jiu Xia, and Yufan Zheng, and it's on the degree of Boolean functions as polynomials over Zn. And I believe, okay, Jiaheng is here, so he will, please, Jiaheng, go ahead and tell us about the paper.
Okay, thank you. So as shown in the title of our paper, we study about the degree of Boolean functions when they are presented as polynomials over Zm. So our main result characterizes the lower bounds on degree and the modular degree for different cases. For example, when f is a symmetric Boolean function, we can argue that its degree modular prime power cannot be lower than p minus 1 times k, provided the input length is large enough, and if the composite modular number is a non-prime power, we provided such lower bound which tends to 1 over 2 times n when p and q are large enough. And on the other hand, we also extend our results on the degree modular p to the k to general Boolean functions as long as it is non-degenerated. That means it does not have any downbeat. So our lower bound is the same, but we require a much larger n or the input length for our lower bound to work. And we conclude with some new conjectures. The first is that we guess degree modulo m can be no smaller than n over 2 for all non-trivial symmetric Boolean functions, and one cannot hope to improve the 1 over 2 factor because we have already provided a tight instance. And due to Guess and Roche in the last century, they conjecture degree f for all symmetric Boolean functions can be no smaller than n minus a constant. Yet the best lower bound is due to the prime gap, which says n minus O n to the 0.525 lower bound. And the last conjecture is due to Goplan, Lovat, and Shapika, who guess the degree is polynomially related to degree modulo m, provided m has 2 different prime factors. If this conjecture is true, then degree m is polynomially related to many other common Boolean function complexity measure. For example, the degree, the sensitivity, the block sensitivity, also on. Yeah, that's our main result.
Thank you, Jiaheng. So we can take some questions again.
I think If I recall correctly, there is a question on Slack.
Okay, yeah, there is one question on Slack, so we can take one. It's Marcus again, so perhaps Marcus, you can ask.
This is more, yeah, so it's more of the Dunbar questions, but maybe interesting. So assume you know that the number has 3 prime factors. Can you get some, of course you cannot improve by too much, but can you get some improved bounds?
Actually, we haven't think about it carefully because we do not know whether there's a so-called periodicity lemma for three periods. You know that the periodic lemma for two periods is when n is greater than p plus q minus 2, then the function must be a constant function. But we do not know how to extend this lemma to the case containing three different prime periods. Yeah, and we don't hope, and we do not hope such argument can improve it a lot.
Okay, so this means that the bottleneck is this periodicity lemma that.
Yeah, this is the main bottleneck here.
Okay, so when you get a lower bound there, which somehow depends on a better bound there, which depends on the 3 primes, then this would give some small improvement.
Mm-hmm.
Okay. Yeah, thanks.
Thanks. Yeah, maybe I ask a quick question. So in your general bound, the second one looks different from the other two, like it doesn't depend on n. Sort of, can you give some intuition about why that is? Jiahe?
I'm sorry,
are you?
I just yeah. I come back.
Okay, good. Yeah, so I was asking in your slide, the form of the lower bound you have for degree p base p to the k is different from the other two in that it doesn't seem to grow with n. So can you give some intuition why that case is so different from the other two cases? I mean, do you expect this to be the correct bound, or is it just the way that the proof works?
Yeah, we provided some tight instance for this lower bound to be achieved.
I see. So you can have functions that depend on arbitrarily many variables, but the degree doesn't grow because of some symmetry.
Yes.
Okay.
So I also guess that's the main reason why the that's possibly one reason that the AC03 circuit is much different from the AC06 circuit.
AC03, but I was asking about this. Okay, yeah, sure. Okay.
Yeah.
So what would be an example for, like, for example, when p equals 3 for a function that attains this bound, like, so degree 2, but depends on symmetric on all the variables?
Could you pardon?
Yes, I was asking. So you mentioned that the bound in the second case is tight. So I was asking what is the tight example? For example, when p equals 3.
Let me think about that.
Okay, yeah, it's okay. Well, I was just wondering
it's just a modulo function.
Just modulo function, modulo 3.
Yeah, with some.
All right, that has degree 2. Good, yeah, that has degree 2.
Yeah.
Okay, thanks. So do we have any other questions for the last talk of this session?
So this conjectures with the degree m of f is greater than 1/2n. Is it only for 2 prime factors, or does it depend on the number of prime factors of n?
We guess it doesn't. It depends on the number of prime factors because our tight instance contains arbitrarily many prime factors.
Okay, and there is no better if it's only 2 prime factors.
Yeah.
Okay.
Thank you. So this is your last chance to speak up. If not, let's thank all the speakers in this session and everyone for attending and thanks, and hope to see you in one of the sessions tomorrow in the conference. Have a good day.